This is a standard gravimetric analysis problem. In a gravimetric analysis problem, you're generally going to be using a precipitate to work back to identify either an unknown reactant or a percentage of a substance in one of your reactants. In this case, you have 0.753 grams of an unknown compound which contains barium ions. That compound is dissolved and treated with excess potassium sulfate. The reaction yields a precipitate of barium sulfate, and the precipitate weighs 0.431 grams. The question's asking what is the percent by mass of barium that exists in the original compound. If you are going to be looking at the percent by mass, that's going to lead you to understand that you need to be using a percent composition. And a percent composition is taking the mass of a substance, divide that by your sample mass, multiply by 100, and you get your percentage. So what we need to figure out is, do we have the mass of the substance in question? Well, we're asking for the percent by mass of barium. So do we have the mass of barium given anywhere? We do not. We do have a mass of an unknown compound that contains barium. So if we have the compound that contains barium, we then have the sample mass. So the sample mass is going to be 0.753 grams. We just need to determine the mass of our barium substance in that sample. Well, to do that, use gravimetric analysis, which means you use a precipitate and you work backwards. So we can use the barium sulfate precipitate and, using the balanced chemical equation, work back to the substance, the compound that contains the barium ions. To do all that, you need to first have a balanced equation. So write your balanced equation. We know that we have a compound that contains barium ions. We react that with excess potassium sulfate. That yields our precipitate of barium sulfate. Then we also have the potassium ions from our potassium sulfate that are still dissolved. So these are it's still aqueous. So these are all aqueous. All reactants are aqueous. We have a solid precipitate, and then we also have the remaining ions are aqueous, floating around in solution. So what we're going to do is start with the mass of our precipitate. And say, all right, we need to go from grams of our precipitate back to grams of our barium-containing compound. To do that, we need to have moles. So we can relate everything using the mole ratio from the balanced equation. So first, we want to convert grams of barium sulfate into moles of barium sulfate. When you look at the molar mass of barium sulfate, the molar mass is 233.7 grams per mole. We want grams to cancel, so we're going to put 233.7 grams on the bottom, 1 mole of barium sulfate on top. That cancels out our grams. We then can use the mole ratio from our balanced equation to convert from one substance to another substance. We look at the mole ratio and we say we have 1 mole of barium sulfate. So that's going to go on the bottom to cancel out barium sulfate. And we want to look at the barium-containing substance. So then we have 1 mole of our barium-containing substance. And because we need to know in the end the mass, and masses are given in grams, we want to convert from moles of our barium-containing substance back to grams. To do that, we use the molar mass of barium, which equals 137.3 grams per mole. We know that we have 1 mole on the bottom because we want to cancel out the moles of barium. We want to go to grams, so we have 137.3 grams of barium on top. And to 3 sig figs, because our initial masses had 3 sig figs, we would yield, theoretically, 0.253 grams of our barium ion. This number is what would go into our mass of our substance. So then we would take, this would be equal to the mass of the substance, right here. We would divide that by our sample mass, so 0.753 grams of our sample that contains the barium, multiplied by 100, and we find that the percentage by mass of the barium to be 33.6%. Barium in our barium-containing compound.